Welcome to lecture 7.3, where we'll be looking at the law of cosines and some ancillary formulas as well. We're going to look at the law of cosines, some more solving of triangles with different special cases, as we see here, side angle side and side 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 triangles. We're going to look at this special Heron's formula for the area of a triangle, and we are not going to go through the derivation of Heron's formula, but you can find that in the text, or probably much more interesting and shorter and briefer and easier to understand would be to go to YouTube and look up a video. Okay. The first thing we're going to talk about is the triangle side length restriction. And this is just saying that in any triangle, the sum of the lengths of any two sides must be greater than the length of the remaining side. So if we think of a triangle with sides A, B, and C, then A plus B must be greater than C. B plus C must be greater than A, and C plus A must be greater than B. Any two sides, the sum of the lengths of any two sides has to be greater than the third side. Okay. So let's think about a triangle ABC, which is an oblique triangle located on a coordinate system, XY coordinate system, as we see here. Okay. The coordinates of A are X and Y, as we can see here. It could be probably negative XY. And if we think about this, right, we know that the sine of B, using this reference angle here to the left side of the y-axis, and in this right triangle, we know that we could use this reference angle for B, and that the sine of B would be the opposite over the hypotenuse, or y over c. And this gives us the y value, which is the small c, lowercase c, times the sine of B. So the length of this side times the sine of B. And that's just doing algebra. Similarly, we can find the cosine of B equals the adjacent side over the hypotenuse of the right triangle. And so we get the x value is c cosine B by that same thing. These should be relatively simple transformations based upon what we've done all semester long. Thus, we can see that the coordinates of A, instead of being just x and y, we can substitute these values in, which is c cosine B and c sine B. Okay. We can also see that the coordinates of C, angle C, is at A, or this point C is at the value A, which is the length of the side, 0, the y value. And of course, B is centered on the origin. We can also see that the length of line segment AC is this value B that we assign using our notation for triangles, that the side opposite an angle is given that same letter in lowercase form. Okay, so if we want to know what the distance of the line segment AC is, this is the distance between point A and point C, and so we can use the distance formula, which is the square root of x2 minus x1 squared plus y2 minus y1 squared, and again the whole square root of that. Okay, plugging in the values, we get x2 minus x1 squared, y2 minus y1 squared, and then we take the square root of that sum. Okay. If we FOIL out these two problems, we can simplify it to what you see here, c squared cosine squared b, etc., etc. I'm not going to read through that. That's just FOILing out what's underneath the square root sign, and then it's also squaring both sides. Notice we squared both sides to get rid of the square root, and on the right, on the left, now we have b squared. Okay. If we rewrite this, we can see that we have c squared times cosine squared b plus sine squared b. And of course, sine squared plus cosine squared equals 1. So we can substitute a 1 in for everything in that parenthesis, and we get simply left a squared plus c squared minus 2ac cosine b. And this is actually the law of cosine. Okay, so specifically that the square of one side equals the sum of the squares of the other two sides minus 2 times the product of the other two sides times the cosine of the angle opposite of the side we're looking at. A squared equals b squared plus c squared minus 2bc cosine a. Okay, so notice here that you have all three sides ABC, 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 and the angle opposite the side that you're talking about over here. So it's b squared equals a squared plus c squared minus 2ac cosine b, etc. So at least there's some pattern here that's a little bit easier to recognize because you have all the pieces there. At least that's kind of how I organize it and think about it, etc. So let's look at some problems. Make sure you write this down so that you can work on the problems as we move forward. Before we go to the next slide, note if cosine of c, or more specifically if c equals 90 degrees, the cosine of 90 is 0, and so this whole term becomes 0, and we just get c squared equals a squared plus b squared, which of course is the Pythagorean theorem, which works on right triangles, which is what this would be. So if any of these angles are right angles, then this disappears, and we simply have, again, a right triangle and Pythagorean. All right, let's look at a problem. This is probably the easiest problem to solve. The law of cosines works specifically with side, angle, side. Two sides and the angle between them, okay? A surveyor wishes to find the distance between two inaccessible points A and B on the opposite sides of a lake. I say this is one of the easiest problems because you've got the diagram here. It's not only giving you all the information in paragraph form, but it's also giving it to you on the diagram. So we can see that point A and point B are on opposite sides of the lake. While standing at a point C, the surveyor, which is here, finds that side B is 259 meters. That's pretty long. Side A is 423 meters. And angle ACB measures 132 degrees 40 minutes. Okay? And so you've got all these measures, and you specifically want to find the distance C between points A and B. Well, this is exactly what the law of cosines finds. C squared equals a squared plus b squared minus 2ab cosine of C. So if we just plug in the values directly to this formula, we can actually solve this problem just by plug and play. Okay, so this is probably the simplest type of formula. I'm not going to, you can try this, you can plug in the values, and in fact, you should try this to make sure that you do get these values. Okay, and so here we see that the distance between the 2 points is about 628 meters. Okay, I guess that could be miles, but that's a pretty long lake if it's 600 miles long. I'm not sure that there is a lake. Maybe the Great Lakes are that long. They probably are. All right, I digress, and let's move on. Solve triangle ABC if A equals 42.3 degrees, B equals 12.9 meters, and C equals 15.4 meters. Okay, so remember that when we're solving a triangle, we are trying to find all of the measures of the sides, A, B, and C. We have B and C, but we do not have side A, so we need side A. We're also trying to find the measures of all three angles, A, B, and C. Again, we have angle A, but we don't have B and C. Okay? So the first thing we can do is go ahead and find the other side. We can do that using the law of cosines. Okay? Since we're trying to find A, we have a squared equals b squared plus c squared minus 2bc cosine A. All we do is plug in the values, get our calculator out, make sure we're in degree mode because this is in degrees. Okay? And we get A equals approximately 10.47 meters. Okay. Now what we want to do here, or actually why don't you think about it for a second. I want you to hit the pause after I ask you this question. Which angle should we go after next? Angle B or angle C, and why? So hit pause and think about that for a minute. And what we're trying to avoid here is the ambiguous case where we might have two triangles, so that we figure out one of the angles and we figure out, well, wait, maybe we could have another angle for this and still make another triangle. And so we want to avoid creating two triangles and then having to figure out which one matches the data given. Okay, so hit pause and I'm going to continue on. So the thing we want to do is we want to pick the smaller angle. Why? Okay. Well, first off, we want to pick the smaller angle because if there is going to be a second triangle, that means that one of the angles is going to be obtuse or greater than 90 degrees, because the only way we can have two angles for the same, two measures for the same angle is if one of them is in quadrant 1 and one is in quadrant 2. And the one in quadrant 2, of course, would be greater than 90 degrees. Okay, so if we pick the smaller angle, then since a triangle can only have one obtuse angle, that smaller angle can't possibly have two angles. And so we know we're going to be building the correct triangle from the beginning. So we want to pick the smaller angle, B or C. How do we do that? We look at the measures of their sides. Since side B is smaller than side C, we know that angle B is smaller than angle C. So the next thing we want to do is find angle B, the smaller of the two sides. Okay, and again, we're doing that so we don't have to create two possible triangles and then figure out which one is the one that fits. Okay, so we can use the law of sines here. We're going to use the sine of A because, well, that's the only angle we have actually. Sine of A over A equals the sine of B over B, and since we're looking for the angle B, we're going to put the sine of B in the numerator instead of having this whole formula flipped around. We're going to plug in the values. We're going to multiply both sides by 12.9. And then, of course, we're going to take the inverse sine of everything on the right here. So we want the inverse sine of 12.9 sine 42.3 over 10.47. And when we do that, we get 56 degrees. Okay? So we now have all three sides, A, B, C. Two were given. We found A. We have angle A and B, and we need angle C. The third angle is always the easiest because all we're going to do is add up all the angles and make sure they equal 180. So we subtract the two angles that we know from 180, and we get the measure of the third angle. Okay, so when we're doing this, applying the law of side angle side to solving a triangle, we can find the other side, and then we find the smaller angle first. We find the smaller angle first. Okay, so notice in this problem, had we used the law of sines to find C rather than B, we would not have known whether we should have used 81.7 or its supplement 98.3, which is its reference angle in quadrant 2. Okay, it's the reference angle. 81.7 is the reference angle for 98.3 in quadrant 2. And then we would have had to build out two triangles, and then we'd have to come back and go, oh wait, this is the one with B equals 12.9. When we found B here, it would be very different from what we had here because the angle would be a different size. Okay? So again, when you're doing side angle side, when you're finding your first, really your second angle, but your first one defined, pick the smaller angle so you don't build two triangles. All right, now let's look at a different case. Let's apply the law of cosines to a side, side, side. Solve triangle A if A equals 9.47, B equals 15.9, and C equals 21.1. Well, again, we can use the law of cosines to find our first angle. We can use any of them. Here we want to use the largest angle again, because if we can figure out what this first angle is, and if it is obtuse, then we know we're on the right track, okay? Again, we're trying to avoid having to build two different triangles, solve two different triangles, and then see which one matches or doesn't match. Again, so here again, we've picked the largest angle this time when we have side, side, side. Pick the largest angle for your first angle, and then solve it, okay? So what we're gonna do here is, here's our law of cosines. We're gonna solve for cosine of C, because then we're gonna take the inverse cosine. We plug in all the values, and we get this value, negative 0.341. You should definitely, instead of just looking at these, try these with your calculator, hit pause as much as you can, try to do it on your own, and then hit play again to make sure you're right. Of course, this is what the cosine of C equals, so we have to do the inverse cosine. And immediately I see it is an obtuse angle because it's negative, and that means it's in quadrant 2, because cosine is negative in quadrant 2. And so when I do inverse cosine on this, I get the angle of 109.9. Okay? So now I have one angle. I need to find my other two angles. I can use the law of sine to find the next one, and it really doesn't matter which one. Here we're going to go ahead and find angle B. We know that the other two angles have to be acute because the largest angle is obtuse. Sine of C, again, since we're looking for the angle, we put the angles on top, or the sine on top and the sides below. We plug in the values, we do our multiplication, and then we take the inverse sine, and we get 45.1 for angle B. And then, of course, to find angle A, we subtract the two known angles from 180, because the angles of a triangle add up to 180, so we subtract the two that we know, and we get 25 for our last angle. Okay. Let's try another problem. Find angle B to the nearest degree for the truss shown in the figure. Okay. So here we have side, side, side again. And in this case, we want angle B. So that's pretty simple. Here, B is 6, A is 11, and C is 9. So we're just going to use the law of cosines with B squared equals A squared plus C squared minus 2AC cosine B. We have all of these values, but if we solve for cosine B, we get this like we saw in the last problem, so that we can find the angle of B. We plug in our values, and then we take the inverse cosine of this quotient right here. Okay, and if you do all that, you should get that B is approximately 33 degrees. Pretty straightforward. I hope that you found that there. I know I went through that exceedingly fast. My hope is that you are actually pausing and trying to solve the problems before I get to them. All right. So now a quick review of the 4 different cases that we saw in the beginning of chapter 7. So the first one was, case 1 was when you knew one side and two angles are known, and this could be either side angle angle or angle side angle. And the steps to solve this is to find the remaining angle by, using the sum formula, that angles of a triangle sum to 180, and then find the remaining sides using the law of sines. Sine of A over A, sine of B over B, etc. If you have two sides and one angle, but not the one between them, side-side angle, here's where you might have the ambiguous case. So you find an angle using the law of sines. Okay, so you find your second angle. When you do that, when you find it, you decide, you look at that angle and the one that was given, add them together, and see if you have enough space to create a complementary angle. Excuse me, I should have done it a little bit differently. So when you find the angle, find its complement, its supplement. This, that's the reference angle. See what its angle would be in quadrant 2, and then add that to the angle you were given and see if you still have enough space for another angle in this triangle, and that would mean that you have the possibility of two triangles. Okay, you find a first angle, you find its supplement, subtracting it from 180, and then see if when you add it to the angle that you were given, if you still have any room, if it's still less than 180. Okay? Once you've found that angle, possibly two, you find the remaining angle using the angle sum formula, and then all the remaining side using the law of sines. And if there are two triangles, you have to do steps 2 and 3 again for the other triangle. Case 3, this is two sides and the included angle. These case 3 and case 4 are the ones that we just did. Here's where we find the third side using the law of cosines. And then we find the smaller of the two remaining angles using the law of sines. This is so we don't get confused and we don't build two triangles. If we focus on the smaller triangle, the smaller angle, then we're going to build the triangle using the data given, and we won't have two possibles that we have to compare. And then, of course, find the remaining angle using the angle sum. Okay? If three sides are known, find the largest angle using the law of cosines. And this will, again, if it is obtuse, it will automatic your inverse cosine function on your calculator will already figure that out because it'll be negative. Okay? And then so you're already building the triangle you need, not building two potential triangles and then trying to see which one fits with the three sides. Find either remaining angle using the law of sines, and then find the last angle using the angle sum formula. Okay? All right, so we have one more really kind of weird formula, and it's called Heron's area formula. There is a very long, not very long, but there is a description of how this is derived, and you might find it interesting. I didn't want to put it in the lecture because it would probably be almost as long, maybe not quite so long, at least half as long as what we've done already, and I didn't want to put that in here. It's in your book, but again, you could also watch it on YouTube or some other channel. Heron's area formula. So Heron's area formula uses the perimeter. It actually uses the semi-perimeter. Now remember, a perimeter, you guard the perimeter. It's kind of the length around something, right? The distance around something. A moat is on the perimeter of the castle. So you might think of, when you're talking about geometric shapes like a triangle or rectangle, the perimeter is the length of all the sides, the sum of all the sides, okay? And so if a triangle has lengths of A, B, and C, then A plus B plus C, what you see in parentheses is the perimeter, and so the semi-perimeter is half of that. So A plus B plus C is the perimeter of a triangle, and times 1/2 is the semi-perimeter, okay? Now to find the area of any triangle, this is quite curious, you can do that by taking the square root of the product of S times S minus each of the sides. S times S minus A times S minus B times S minus C. And this works. It would be, to me, it'd be more interesting instead of just seeing the derivation, be interesting in what was the inspiration for someone to figure this out. Okay, so make sure this is in your notes someplace. You cannot have a note sheet on the test, but make sure it's in your notes and that you know this formula. All right, so let's look at one application of this. This is when you have side, 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 because the area is based upon the perimeter, the semi-perimeter. The distance as the crow flies from Los Angeles to New York is 2,451 miles. From New York to Montreal is 331 miles. From Montreal to LA is 2,427 miles. What is the area of the triangular region having these three cities as vertices? Okay. This is to let you know this is not to scale. This isn't actually the size of the country. All right. So again, the first thing we have to do is to find the perimeter, A plus B plus C, and then actually times it by 1/2 to get the semi-perimeter. Okay. A plus B plus C times 1/2 gives us 2,604. we simply plug that into Heron's formula. Remember, the square root of s times s minus a times s minus b times s minus c, and we should get the answer. The square root of s times s minus a times s minus b times s minus c, and we get 401,664 square miles. Okay, so this is really just a plug-and-play formula as well, to make sure you know how to find the semi-perimeter and then know this Heron's formula for area. All right, hope you enjoyed the lecture, and I'll see you in the next one.